GDPR form. Thinking about the GDPR form for the recording. Can you hear me well? Yes.
Okay, everybody, welcome along to the November meeting of the Astronomical Society of Glasgow. The weather's a lot better this month than last month. It was too dangerous for me to even attempt to come to Glasgow last month, but I've got here tonight without any problems. So first of all, I'm going to pass to David for the Secretary's announcements.
Thanks, Bob. If you could give everyone, there's quite a few announcements tonight. No, if anyone does have trouble hearing me, just give me a shout. Okay, the first event takes place this coming Monday, the 20th of November. Now, this is a public observing night at ECMO, the Observatory of Bath. Now, ESG members are welcome to come along, provided they are willing to help out. Sort of just general help, sort of maybe help with moving equipment or about engaging with the public, that sort of thing. So that takes place this coming Monday. The next event takes place a week tonight. Is 2 weeks tonight. It's a week tonight. Sorry, the 23rd of November is the imaging group. Now, this is a Zoom presentation. It takes place from 7:30 to 9:30 p.m. Again, Sinclair, is there a subject?
There will be. I'll email it probably the day before. I'm working on something at the moment.
That's fine.
But I mean, last meeting it was quite difficult to draw to halt because everybody was contributing, which is great.
Okay, that's great. Great, thanks. The next event is the Observers Group. Again, this is a Zoom presentation which is presented by Robert, which the subject will be the December sky. The links for both of these events will be sent out here at the time. Now, in between our members' events, there's an event taking place on Tuesday, the 5th of December. This is the inaugural Royal Astronomical Society Professor John C. Brown lecture, which takes place at Glasgow University. It's presented by Professor Randall Stevenson. The subject is Celestial Visitants, Comets and Culture in the 19th Century and Beyond. It's a free event, but it must be booked, and details are found on Eventbrite or the RAS website. After that, we have the beginners group. This will be at Acre Road, which is run by Chris and Lorna. The subject for that month will be the moon. That's Thursday, the 7th of December, 7:30 to 9 p.m. And the following Thursday, I do believe there's another observing event at Acre Road. That's on the 14th of December, the same time, 7:30 to 9 p.m. And finally, just another couple of things. We are looking at the possibility of once again trying to hold a Dark Skies weekend at the Blencathra Field Studies Centre. That's in the Northern Lake District. We did try to hold this event actually round about this time, but we couldn't get enough interest. We weren't able to raise enough numbers. We are going to try again. There is a list here, and if anyone is interested in taking part in a weekend, it would probably be around sort of mid-March through to sort of any time from there until sort of mid-March. There's no need to commit yourself, but if you are interested, just put your name down and we'll see if we can get enough numbers to actually run that weekend. And finally, you might have mentioned we've brought along some merchandise. There is actually a sale at Red Bottle at the moment, which is where we sell our merchandise. Details can be found on the website, and also if you are interested in buying any stuff tonight, if you see our treasurer Jim, who is somewhere there he is.
I'll take the money.
Okay, that's fine. And I think that's it.
Okay, so we can now move on to the main part of the meeting. And it's my great pleasure to introduce Dr. Gilles Bailet, who is a research fellow of the James Watt School of Engineering at the University of Glasgow. And he's into emerging space technologies, and he's going to talk about micro to macro space technologies at extreme lengths of scale.
Thank you very much for the introduction, and hello everybody. So today I'm going to do something a bit different from the presentation you might have seen from other space engineers. I'm going to spend the first half of the presentation talking about advocating for space engineering. And then I'm going to go on to my research and talk about those emerging space technologies. So I've done many things in my career, and the main part of it, so are two pillars. The first one is regarding planetary exploration. So I was in charge of designing re-entry systems. So what you can see on the picture, so on the left part, the lower right picture, is the first object I sent to space, so that's a CubeSat. It was 5 kilograms, 34 centimeter length, and that was actually doing what shooting stars do. That was re-entering into the Earth atmosphere, burning up, totally destroying itself. And the goal of that was to be able to gather some data, to be able to build more efficiently, with lower costs and more reliability, the next generations of re-entry vehicles that will bring back humans from the Moon or Mars. And we had great success with it. So the picture of the instrument you see just above is an emission spectrometer that flew on this mission. We got great results from it, and now it's actually considered to fly on board the penetrator that will go the mission to Uranus. So we are hoping to get selected for that. We are working with a European team, and hopefully we will be able to have a Glasgow instrument onto this mission. And the three pictures that you see on the left, it's, I have a lot of emotional attachment to that. It's what I did during my PhD thesis. And the idea was to really try to understand the dynamic of re-entry. So when an object goes through an atmosphere and burns up, most of them survive, some of them do not survive. But we really wanted to understand the behavior of the transportation system matters on it. And so the second part of my research is to deal with emerging space technologies, and in particular dealing with in-space manufacturing. So 3D printing things directly in space. So you will see later in the presentation why this is game-changing for the industry and why I'm so excited to work on this topic. And just before we move to the rest of the presentation, I've been traveling a lot of my career. I've been working a decent amount of time at NASA in California, and I can tell you that we are really lucky to be here in Glasgow. So Glasgow is really exceptional in the world in terms of space engineering. And myself, I have my house, my office, my laboratory, my favorite spacecraft manufacturer, my favorite whiskey pub, all within 20 minutes walking distance from each other. And this is really game-changing when you're trying to do ambitious projects, when you are really trying to collaborate in different manner. And it's really easy for me to pop into the office of a collaborator to be able to discuss how to integrate my instruments, or to just discuss on how to write a bid. And actually, just after this presentation, I will run home to finish a big bid that we have for tomorrow noon. So why I'm doing this presentation usually is to try to really push a different way of doing outreach for space engineering and for space in general. Because there's a lot of money which are spent in the space segment, right? And you will always find people, maybe not tonight because most of you, I hope, love space, but in general, you will always have some people that will be concerned about the amount of money we are spending in the space industry. We're going to ask why do you spend so much money when we have huge waiting time at the NHS, when there is hunger in the world and things like that. And so the object of this short presentation, humbly, is to try to actually push a narrative point, but we'll explain why it's actually so important to invest in this field and to go work in this field. Not just to be space engineers or scientists, but actually everybody can contribute. I have friends and colleagues which are secretary, accountants, or many other jobs, and they're actually directly contributing to the advances of space engineering and humanity in general. And so the talking point that you're seeing in general for the space industry and UK Space Agency, usually they are using those talking points. If they are showing you those, bright rockets, those bright new astronauts, they are doing a lot of cons around that. You might have seen a few weeks or a few months ago, they brought a mock-up of a rocket in George Square to do some outreach about space engineering. And they're showing like, look, we have that, it's really nice, and it's why we are doing space engineering, why we are putting that much money. But for me, I love space, right? But even for me, it's not satisfying of an answer. And for all those people which are, crumbling under debts, not eating enough, or waiting on the NHS waiting list, it's not a satisfactory answer, right? Just to give you a number, the cost for the UK taxpayer for the space engineering we are doing, the whole of UK, is about £1 per year. So it doesn't really seem like a lot, and it's not really a lot compared to the overall budget of the UK, but it's still something that we need to justify, right? We need to justify why we are spending so much money. So the first two examples I'm going to give you are general examples, and then I'm going to try to make it more relatable to you. So something that all of you have used already, I hope, and I know that I've used that to come here to this building today, is the GPS, which is working with satellites orbiting around Earth, and you're able to triangulate your position thanks to extremely precise clocks on board those spacecrafts. And those clocks are actually super helpful for many, many other applications. Every time you do a bank transfer between different banks, you are using those clocks to have a timestamp on those business transactions. Okay? But we are also using those clocks on board the spacecraft to be able to do many, many different measurements. Among those, something that you are often hearing about, which is the rise of the sea level. Maybe at least once a year you're hearing that, okay, like in 10 years it's going to rise by 1 meter, Glasgow is going to be underwater or something like that. And those measurements, the way we are tracking that is actually thanks to reflectometry, where the signals of GPS satellites will reflect on oceans, seas, and lakes, and we'll be able to track this rise of water. Something which is really popular in the UK to talk about is weather. So we all have already had these awkward conversations when we are talking about the rain or something like that, right? And the big thing that the space segment is really contributing to is not just predicting if you need your umbrella or not, but actually predicting catastrophic events that will happen, like typhoons or cyclones. And something also really important and many people do not know is every morning pilots, airports, and airline companies, they look at the weather predictions to be able to affect and slightly modify the travel plans of the aircraft. So here again, we see that the spacecraft are actually the only one able to cover and monitor the weather all around the planets. And so it's the only way we're actually able to predict those weather patterns and able to predict the modifications we have to do on the aircraft's travel plan. Something which is actually always really interesting for me to show people is when we talk again about this argument of we should stop putting that much money in space exploration and putting all of that into solving world hunger. Actually, the space segment is doing so much for food security. So here you have an image that was taken by the constellation of Earth observation spacecrafts. The constellation is called Copernicus, and there is a lot of work done on that for Europe, including the UK, where they are actually able to predict in advance what will be the weather pattern that will happen on your crops. So what will be, for example, the surplus of rain or the drought or things like that, and how it will affect the crop yields. So you're actually able, with science, using those space images, to be able to monitor the health of your crop and be able also to predict the crop yield you're going to have. And here what is really interesting, so in the picture on the left, you're able to see some different things like, for example, some rain surplus or some rain deficits. What is really interesting for me is that in the UK, they're actually not predicting any rain surplus, that actually usually make people surprised about, but I guess it's because it's raining all the time. There's no room for that. But here we can see that being able to monitor that, you will be able to see that those areas in the east part of Europe will be actually affected by the weather patterns. Right? So here you see that you will need to put in place some logistical ways to actually solve the food security issues that you can see. So you need to bring more, for example, more food onto those areas to be able to make sure that people there get enough food to be able to survive. But the really good thing about space is you do not need to just be a rich farmer, have your own UAV or your own aircraft to be able to do your own measurements. Here, with a constellation of a few dozen spacecrafts, you're actually able to do this exact work for the whole of Earth. And this is really something fantastic because it means that you can help countries that do not have the money to have a big space industry to actually access to food security. So there's still a lot of work, and I think for me the biggest barrier is not the capability that we have as an engineering and scientific community, but actually the issue that we have on the political side. So we have all the tools in the science and engineering, we just need now some critical will to be able to solve those issues. So the issue is not that we are spending too much money in space engineering, the issue is that some people are not maybe taking the right decisions. So now something which is really exciting to me, because it's linking with the collaboration I have with NASA, is regarding being able to predict volcanic eruptions and predicting earthquakes. And this is something that is really interesting. So in Europe, we are fairly rich countries, right? So we're able to actually put sensors into volcanoes. And you might have heard about the Mount Etna or in Italy, or some volcano that recently started to erupt in Iceland, where they're actually instrumenting heavily those volcanoes with instrumentation to be able to actually predict in advance when something bad will happen, like an eruption or an earthquake. And this is actually something that now will be accessible not just for rich countries or for charities, for example, that will invest money in poor countries to put those type of instrumentation, but you will actually be able to do that using high altitude balloons. So the idea of those high altitude balloons is they're going to use NASA technologies which are under development right now that have been designed to explore Venus. And the big issue on Venus is that you have a really thick layer of clouds that do not really allow you to see clearly what is at the surface in every wavelength. And so these balloons that will explore the Venus planets will be equipped with microphones. And those microphones have been designed with a specific algorithm and a specific measurement technique that they will be able to actually pinpoint Venus quake events on Venus directly from the air, from high altitudes. Okay? And so now they are working also on trying to shift those technology back on Earth, and they're actually doing some tests to validate this technology for Venus. They're doing the tests on Earth with balloons going from Europe to Canada. And this will be able to deploy, a constellation of high altitude balloons that will be able to take this kind of measurements and predict this type of catastrophic events anywhere in the world with just a little amount of money, because for each sensor is actually 2 microphones. And so now, maybe it's not rateable enough for you. It doesn't have a strong enough impact on your life. And now we're going to move to some maybe more personal examples that I find really, really interesting, and a big effort that NASA has been doing now for a few decades. It's to try to collect how the technologies developed for space missions, which have been developed because those environments are so extreme that you need to solve problems that you never have seen before. How those new technologies then come back to Earth and are used for other applications. And they've been able to gather more than 1,800 examples that shows this type of spin-off technologies. And there is this fantastic website that you can go and visit to explore the portfolio. And I really want to advocate on the fact that I think we should do the same thing in Europe here, to try to really explore what was the impact of our space technology. We have some bright examples here and there, but we don't have all the catalog to actually show the public why they are investing that much money into the space industry, not just for beautiful pictures that make me dream so much, but the idea is to see how it can impact everybody, right? So now, some of the fun examples. So we actually have a big champion in the UK, which is located in Wales, which is called Spaceforge. And they're going to actually be able, right now, in a few years, to produce some high-value materials in space, because space is ultra-high vacuum, ultra-clean, things like that, compared to laboratories. And they will be able to grow crystals in microgravity, way bigger than what you can do on Earth. And so, for example, for people with which are diabetic, they need, in general, to have 3 shots a day of insulin. If you actually growing those crystals in orbits, instead of 3 times a day, they will need to have an injection only 1 time every 3 days. So you can clearly see here the impact that it will have on the standard of living of those people. You know, you can have a really different way of living, you can go on trips way easier, you don't have to worry so much about taking your drugs and things like that. Another thing here that actually we are using during the presentation with the camera here is a digital camera. And the origin of the digital camera was for the need of spying during the Cold War. So the original idea was that one day the US wanted to spy on the Soviet Union. They were launching some kind of missile in space, so Cage missile, and they were taking some pictures with traditional argentic films. And then they needed to dump this film with a re-entry capsule, right, back on Earth. And for having worked in the field of re-entry vehicles for now nearly 15 years, I cannot tell you how complex this is to be done now. So imagine how complex it was in the 60s, right? So you need to be like really good at doing a pinpoint landing into a specific location. You need to make sure everything survives. You need to make sure so that inside your capsule, the temperature will not go too high, otherwise you can fry your film, right? And so now this needs emerging from the space engineering is in the pockets of nearly everybody in this room, right? So something which is very exciting to me is the exoskeleton. So you've seen maybe at the beginning there were slides with a Mars Curiosity rover, where actually they put a rover on Mars. It costed $1 billion. So much money, right? But there are so many advances within these robots, and one of those that we can directly see the impact now in the science, but also we are starting to see that as products that you can buy, was our exoskeletons. So you might have seen recently there is a company that started to produce exoskeletons that can help people working in factories, so that help reduces the load that they have when they try to carry some loads, right? But this same technology can also be used for people with low mobility, and even down the line for people which are paralyzed. And all of that is actually enabled by space technology, because when you go to space, when you send a rover to Mars, every kilogram, every ounce of mass you send to space is extremely expensive. So now, even with the bigger rockets, you can estimate the launch cost plus the paperwork and everything will cost you something between $8,000 and $10,000 per kilogram of mass. So if you want to send a rover to Mars with maybe 20 motors inside, you want to be able to have those motors as small as possible, as light as possible, but also as powerful as possible. And this is really the game changer for those exoskeletons, to be able not just to have really big motors everywhere around you, but to have miniaturized motors within your exoskeleton to be able to carry loads, but also not be too cumbersome. Another one that I really like, which is I think really exciting, is dealing with hydroponic. It's when you want to go to explore Mars, to live on the moon, or to live on Mars, or even beyond, you will need to be able to grow your own food, right? And so something which is really interesting is our sun is white. When it goes through the atmosphere, it becomes some kind of shade of yellow, right? But the plants, you're seeing it as, most of them, as green, because it actually reflects most of the wavelength, of the green wavelength of the spectrum of light, right? So it means that all those green lights will not contribute to the energy of the plants to grow. So it means that it's energy wasted. So actually researchers have been working a lot on trying to optimize the power budgets of their missions to be able to really optimize how much energy you are putting in the plant to grow and then to eat. And this is so important because, again, of the mass and volume constraint of space missions. And so now we've been able to develop some new LED technologies to be able to actually more efficiently grow plants. And we are starting to see some startups and some small companies that are going to start to grow plants inside the cities thanks to the economical viability of this type of agriculture. So there is also something recently which is really exciting is regarding Alzheimer's. So they were able inside the International Space Station to actually understand the real mechanism of the disease. So they were able to really understand that actually surface tension is playing a huge role into that, and they will not have been able to understand that on Earth. And so now that they really understand the mechanism, they have some ideas for treatments. So hopefully they're going to be able to have a really potent, efficient drug to be used to fight Alzheimer's disease. And something more trivial, which is I always like to put it here, the non-stick pan, right? Most of us have used that to cook, for the one of us that cook, and this is basically the Teflon pans. And this has been used, and this is a major advance in space mechanisms. Because when you want to send some really large and complex missions, you will want to deploy some appendages. So deploy some antenna, deploy some solar panels or things like that. And to be able to have a deployment, you need an hinge, right? And so on Earth, for example, if you are looking at a gate, you will have a simple hinge which is metal on metal, right? But in space, if you are doing that, you're going to have what we call cold welding. Those surfaces will start to stick together, and they're actually going to fuse together on the crystalline structure. And so to be able to combat that, to avoid having your different parts sticking together and not being able to deploy, space engineers have deployed some novel polymers. And so this one is Teflon. Teflon is a brand, the real name is PTFE, that have been developed to be able to actually act as some kind of lubricant, solid lubricant between surfaces to be able to work correctly. Okay? And two last examples that I really like. So the first one, I think, saved at least one life in every family. It's a dialysis machine. So some of you already might know that. So dialysis machine, the original technique was a machine that was used for the Apollo program where they needed actually to save water. So the mission was 1 week. So instead of sending enough water for the 3 astronauts to survive for 1 week, they just sending enough water for them to survive a few days, right? And then what they needed to do once they drank the water, they would pee it and they recycle it, right? So it's a bit of the same thing you can see in the movie Waterworld, the same idea. And so from this idea of saving water and drinking your own pee, they really were able to emerge novel technology to actually filtrate blood to be able to actually save lives. And the dialysis machine is saving hundreds of thousands of lives in its existence, and it's still starting to make new progresses now. So you have better filtrations, but also we are starting to see transitions and spin-off from this technology to be able to solve water security in the world. So in some poor countries or after disaster relief, you always have some issues with water. So you have a lot of people which are dying because of illness which are contained within water. You have pandemic that are going to be spread through filthy waters. And actually now they are starting to miniaturize the technology to be able to have these water filtration systems without any moving parts. And that will be actually developed thanks to some new work that have been done for the Mars colonization and life on the moon, where there is no moving part and is done thanks to nanotechnology and new ceramic manufacturing. And the other one that I really like, the original name was really bad, so that's actually the diver, right? So the idea was that when you're gonna spend so much time in space outside your space vehicle, so some EVA, some extravehicular activities can last up to 16 hours. You might have some bodily functions that you need to go, right? But a spacesuit is actually equipped with a really complex electronic system inside to be able to regulate your temperature, to be able just to keep you alive there, right? But if you are starting to pee in your suits, you can actually fry it completely. And actually that's what happens during the Gemini era, not in the spacesuits, but somebody was seated in their rockets, waiting for the launch, and as launch do, they had some delay. And they had too much delay for them, they needed to remain seated into the rockets, they couldn't, and they just went number one. And actually some of the circuits, some of the vital circuits of the rocket fried them, right? So they had to actually postpone the launch not for a few hours, but for actually a few weeks, if I recall correctly. And so again, for me, that's why it's so important to advocate for space engineering. And it's something that, you are all here passionate about astronomy. And I understand you so much, I'm a really big space nerd, I love that so much. But our mission is not just to show beautiful pictures of the stars to people, but really to make people understand why this is actually so important. To inspire people, through astronomy for example, but also to make the quality of life better for everybody on Earth. And again, this is not just a job for space engineers. Everybody can contribute to space engineering, from secretary, accountants, technician, everybody. It's not just old professors that are doing the changes, or people at NASA, it's really everybody. And we are seeing more and more citizen science and hobbyists actually playing in the field, trying to improve things. And thanks to the CubeSat standard that actually Glasgow is leading the world, we are seeing actually some spacecraft starting to be affordable for clubs of hobbyists. And in the UK, actually, they are really good at that. So there is AMSAT UK, which is the Association of People for Amateur Radio, that actually flew several spacecrafts to be able to do some radio relays. And they were able really to funnel a pipeline of talents from people that were passionate about radio to actually people that then had more impact into society as engineers, for example. And so now that I talked to you about that, and now that you're going to transmit the good word, I'm going to move to what we are doing at the University of Glasgow. So this is a slide I stole from my boss, Professor Colin McInnes, but I really like to actually show why academia has such an important role in this type of novel technology that then we can spin off to Earth application. So if you ever attended a meeting with an academic, you will see that it's a nightmare for brainstorming. We have dozens of ideas a minute, right? It starts to be too complex at some point, but you have to stop having ideas and start to actually test things. So it's what will happen. In Kaya, for example, you will have 3,000 water cooler ideas. It's an idea you can have just at a small, in a small conversation or something that you will have at a meeting. From that, you will select some of those that seem promising and people like, and then you're going to put bid for a small amount of money, you're going to test it if it works or not. You're going to get some of those projects awarded, they're going to start to be some running projects. Some of them going to actually be pretty nice. We want to develop that to the next level and actually maybe fly it. And so you're going to have maybe 4, 5, 6, depending on how successful you are, projects that you will be able to send to space. And among those, we are expecting that among those 3,000 water cooler ideas, you might have 1, 2, 3 major success that will actually change the way space engineering is done or have a direct impact on society or the UK space industry. And it's really what we are trying to do. So our team at the University of Glasgow, so we are hosted by the James Watt School of Engineering, which is part of the Space Glasgow Research Network, which is also taking account people from physics and astronomy. And we are hosting a total of 25 research staff and PhD candidates. And we have a few labs, so we have one lab which is called the ISET lab, which is on the top left, which is where we are doing our bench work. Right? We are testing some small ideas, doing some small prototyping, a lot of 3D printing, a lot of issues, a lot of mistakes with things, and it's directly hosted within the James Watt School of Engineering. Then we have the Acres Road facility, so this is near the observatory of the university, where we have a really large vacuum chamber. So this is the picture which is on the top there. You see a person for scale. And this is a really large vacuum chamber which is able to do dirty vacuum. So it means that you can put contaminants within the vacuum and you will be able to keep the same level of vacuum. So that doesn't really mean anything like that, but the way we are using it is actually really interesting. So the main focus of that is to be able to study the dynamic of rockets or landers, either landing or lifting off. And all the interaction of this really big plume of hot gases that you can see on videos of rocket launches will interact in a really specific and really strange way when you're going to go on the moon or Mars. Because there the gravity is so much lower and there is not really a real dense atmosphere to be able to slow down those particles when they got ejected. We really need to do a lot of research with that. And we are in the process of having a Space Act agreement with NASA to be able to collaborate with them on that, where we're going to really try to understand the dynamic of those rocket launches and landing. Then we have a facility at Govan on the south side, where we are doing all the work related to exploration of the surface. So we are doing mostly deep drilling. So the idea is to be able to do drilling on the Mars or the Moon to get samples and things like that. But the idea is also to try to help the British Antarctic Survey to drill the bedrock under Antarctica. And we have two of our PIs which are currently in Antarctica doing some testing for the new generation of the driller. And we have finally another facility which is called MAC. This is up in the islands inside the old Air Force base. And the really nice thing about Air Force bases is that they have those big concrete kind of shelters, I would say, big concrete shelters that can resist to bombs. But if it can resist to bombs, it can also resist to experimental rockets exploding. And our researchers are actually doing some novel type of rocket experiments there, where they're able to test new technologies. So for example, we have a really cool new technology, which is that the rocket eats itself when it's going to lift off. So the idea is that the carburant of your rocket is not just the hardware you are putting in it, but also its structure around it. So the idea is that, the big idea is that when you're going to lift off this new rocket, when you're going to arrive to the correct orbit in space, you will only have your spacecraft. All the rest of the rocket will be totally consumed. So you are really this is the top of what you can do in rocket optimization. And so along those research work, we also are really lucky at the University of Glasgow to have two fantastic student teams. So we have Gilles rocketry, which are specialized in doing small rockets, and they are doing a lot of competitions, and they are working really well, and then they are going to get some really nice jobs in the rocket companies we have in Scotland. And also we have Geo Orbits that won 2 years ago the first competition of the UK Space Agency for students, and they won £600,000 to be able to build and fly their own spacecraft. Okay, so we are really excited about that. They're going to build it inside our laboratory, and they're going to be able to launch it in a couple of years. So within this excellent environment, we're able to actually cover the whole range of space missions. From, again, access to space with novel rocket technologies, orbital dynamics with giant space mirrors, with solar sailing. We got my research team, which is with emerging technologies. Then we get exploration technologies with deep drilling. And finally, we get re-entry and landing, where we are also taking into account how the astronauts on the moon are going to be able to operate. So we are also trying to develop some new tools that can deal with the electrostatic particles on the moon, which is the lunar regolith. And we have some nice successes. So we had a really fantastic flight from our students 2 years ago when they went to a parabolic flight in France. So this is a plane which does parabola. And when you're at the top of the parabola, you're experiencing 20 to 30 seconds of microgravity. So you can actually test space systems that will be able to give us some new knowledge in those environments. And for that, we were working with some really tiny spacecraft, and I talked about a few slides, but we are calling femtosats, and the idea was to validate that those tiny spacecrafts, which are the size of a matchbox, can actually orientate themselves in space. We're going to also have a launch of my in-space manufacturing technology at the end of next year from a rocket, and some other really fun stuff. So within the Emerging Space Technology Group, we have 3 main grants. So the first one is a share from the Royal Academy of Engineering of my boss, so Professor Colin McInnes. And here the idea is to really explore the extreme of the name scale. So to explore the really tiny spacecraft, the one I just talked about, which is a picture on the far left, but also to explore the giant structures that we can build directly in space. And this is the effort I'm leading. Colin also won a ERC Advanced Grant, which is a grant from the European Commission, to be able to explore a new kind of spacecraft, a new kind of constellation, which is a constellation of really large, flat mirrors. So those mirrors are going to be 250-meter diameter, so large, right? And they're going to reflect the light of the sun onto photovoltaic farms on Earth. So the idea is that we already have farms on Earth which are 1 kilometer wide and that host, all those solar panels. And the idea is instead of adding more solar panel farms on Earth, we can just dump more sun onto them. And the idea is exactly that, is to increase the share of green energy into the total energy mix that we have. And finally, we got a new UK Space Agency project, which is dealing with making in-space manufacturing and manufacturing for space more sustainable. So we're going to test in space conditions some advanced materials to make sure that when we're going to build giant things in space, it's not going to break up in thousands of small debris and totally contaminate the whole space environment and contributing to the space debris problem. We're going to be able to do this new type of technology in a more sustainable manner. So now let's dive a bit into the micro theme, which is those really tiny spacecraft. So if instead of traditional bird-sized spacecraft or traditional CubeSat shoebox spacecraft, if you had something that you can hold in the palm of your hand, which is 50 quids a piece, that you can launch by the thousands, how that could change the way you do space engineering. So this is exactly the prototype that we have. So this is the self-contained spacecraft. This one weighs 30 grams and is able to be fully autonomous and orientate itself alone in space. And by itself, it cannot do much, right, compared to a big spacecraft. But the real value is when you start to deploy them in a flock. And so we are starting to do some experiments in the lab where we have 40 of those chipsets, and we are starting to do some distributed measurements things. And here you are starting to really change the way you are approaching the space science. So instead of having few spacecrafts which are able to take high resolution images maybe every half an hour or something like that, what is happening if you're actually deploying thousands of them and you're able to have a high resolution in time and position of the data in low resolution. And actually we are seeing some really interesting things where we are able to really track super well some phenomena that happen in space, so for example some space weather phenomena that will happen, but which happens really fast. So for example, if you just have your traditional constellation of spacecrafts and you have a solar eruption and you have an interference with the Earth magnetic fields, you will have only few data points of these events. You will not really be able to understand the complex 3D dynamic and the way the magnetosphere of Earth responds to its solar eruption. But with this technology, you're actually able to recharacterize with a really fine granularity what is happening there. And then we have some a bit more fun and more simple to do, where we're actually using this tiny spacecraft as a selfie stick for space. And this is actually really important for industrials. So a lot of industrials have really complex deployable structures, so deployable antenna, deployable solar panels or things like that, but they are actually not always working properly. But they don't really have the equipment on board to be able to correctly understand what is happening. And so for example, if we are looking at history, I think it was 10 years ago, we had a really, really big spacecraft that was the size of a bus from the European Space Agency, which is called NVSAT, that had an issue in the deployment of beams, and they were not really able to understand what was happening. And they had to do radar images from ground to be able to understand what was happening, right? And here, if you have this deployable selfie stick, you will be able to actually image your full spacecraft with enough distance to really be able to understand what's happening there. So now let's jump to the other side, which is a macro thing. So how would you do space engineering differently if you will not have the constraint of the rocket? Right? Because again, the constraint for space engineering, what all space engineers learn in school is that the big constraint is the mass and volume that you can lift up into space with the same rockets. And it's exactly the reason why the International Space Station looks like the way it looks like, right? It's different modules which are the diameter of the space shuttle, or the diameter of Ariane 5, but are assembled together, you know? And it's actually not optimized to be a space station. It's optimized to be assembled in space for modules which are launched with rockets. But what is happening if you can build all of that direct in space and you don't have this constraint anymore? But if the only thing you are sending in space is not your spacecraft, but it's actually the feedstock to build your spacecraft. It's exactly what we are working in my team on. And one of the main projects that is driving that in the UK is what we call a space-based solar power. So the idea is you're going to collect all of this energy from the sun with a station that will be in the geosynchronous orbits, and you will then pull down the energy through microwave on ground. And the idea is to ensure energy security without having some nuclear power plant on Earth or depending on fossil fuel on Earth. So be able to have those giant stations. And this is huge. This is 13-kilometer wide stations, 2.9 gigawatts of energy, and the cost, £8 billion. So this is, you know, major investment, crazy sizes compared to anything we've done before. And when you are looking at the way the UK is preparing for that, they are trying to put in place some roadmaps, and the same thing is happening in the rest of Europe with the European Space Agency, but in China also, and in NASA for the US. And they are all putting in place these kind of things, but we cannot expect to develop capabilities that from today to 2040 will be exactly able to build those giant stations. We have to have stepping stone towards that, and we cannot just pour billions in this industry to just do demonstrators, to demonstrate we can build like bigger beams or bigger panels or whatever. We need to have something that makes more sense, right? And so before I just go in the way we are tackling that at Glasgow, I just wanted to give you another view of the way we do space engineering in the world. So we have, again, those companies which are producing really high-value materials in space, like insulin, or you can grow semiconductors in space, like diamonds or graphite and things like that will allow you to have electronics that will use less energy. You have also the traditional in-orbit subtractive manufacturing. So basically, you are doing exactly what you do in a workshop on Earth, but you are doing it in space. And this is really nasty, because in space you have microgravity. So all these sheets of metal that you're gonna take away from the part you want to build, gonna start to fly everywhere. So this is a major issue. You have also in space manufacturing covers building of infrastructures. And here we are talking, for example, of building launch pads for rockets to the moon, building habitats to the moon, and other fun things like that. You have also in space assembly. And here again is the old school thing. So the idea is you are just lifting off modules that will be assembled together. And again, we don't really have any optimization there. But actually what is really interesting for me is the first demonstration of in-space manufacturing. It's something that really sounds like futuristic, right? The first demonstration was done in 1969 by the Soviet Union, where they were actually doing some soldering. And when you think about that, soldering is adding some materials to a part that already exists. So that's additive manufacturing. And they actually did some fantastic work there. And so now we have also some companies which are really trying to optimize the process on Earth and to make it suitable for space. And most of them, what they are doing, that is, they are 3D printing metal, or they are 3D printing polymer. What they are trying to do is just to take machines that work on Earth, make it work in microgravity within a confined environment with an atmosphere. And actually something which is really interesting to me is NASA paid millions and millions to a US company which is called Made in Space to try to assess what was the influence of microgravity on 3D printing, and the answer is none. Actually, the issue, if you want to 3D print in space, is not microgravity at all, is the hard vacuum that you have in space. That poses a lot of issues with the thermal environment of a part and the way, for example, when you're melting your plastic, the way this plastic cools down. And so it's exactly what we are working on at the University of Glasgow. And I'm just going to go a bit fast with that. And it's exactly the same thing. They are just trying to take things that works on Earth and make it space-rated and fly to space. And we do believe that this is not the way we can innovate. This is not the way we can push the limits and then bring back those technologies down to Earth, right? And the main issue also that we have is the competition, the industrial competition. So these big companies in the US, what they are trying to do, because this field is so new and there's so much money into it, the UK estimates by their own roadmap that we have a market which is worth $1 trillion within the next 20 to 30 years. And so those US companies, they got this huge investment from NASA, hundreds of millions of dollars to develop their technology and to fly their demonstrators. And what we are trying to do now is to patent all of the field. So they are trying to patent anything that exists. You can look at the list, it's very crazy. And then the idea is that even if those patents are not viable in the UK and Europe, so most of those patents actually are not awarded in the UK, but because of the way the US patent law is framed, those patents actually still hold in space. So now if I'm coming here and I say, oh, I want to print my giant mirrors in space to make more green energy, actually they're going to tell us, oh, no, you can't, it's our technology, even if it's not, and that's going to be a major issue. So I was hired 4 years ago to really tackle that. And when I arrived 4 years ago at Glasgow, I started to see actually what was the roadmap from the US, what they wanted to demonstrate to be ready in 20 years to build those giant 13-kilometer wide stations. And the only thing they're doing now is they want to actually 3D print 10-meter beam. And it actually doesn't make sense. They got $100 million for that. And in the UK, we have a company which is called Oxford Space System. They can produce you a beam, a 10-meter beam, from something that holds into your fist, right? So they are using bistable beams made with carbon fiber, and they're able to do exactly the same thing. So no one gonna buy this 3D printer if it's just able to do 10-meter beam, right? So we really have to change the way we are approaching the problem. We have to find a minimal viable product soon that the industry will be able to adopt, to be able to start producing real things in space which are useful for society, useful for the companies, and then with the years we'll be able to progress, to earn some flight heritage, to push the technology, to build bigger things, better things in space. So then we'll be ready for those really important for the energy, really important stations for the energy security. And so it's exactly what we are doing. So we've developed a full range of technologies at the University of Glasgow that can go around the patent-enabled monopoly of the US. And the two first patents are actually contained in the shiny box. So the patent should be out in 6 months. You can go on Google. In 6 months, Google Patents, Google me, and you will find those beautiful drawings. And so those two patents will be published in 6 months, and hopefully we're gonna fly this shiny box in space at the end of next year. So we are really excited about that because that will really underpin the work of our efforts. And the next step after that is actually to find this minimal viable product that I tell you. Because if the space industry start to appropriate themselves this in-space manufacturing technology, then we'll have a huge boom, right? We'll be able to attract more money, to develop better products, and then to have more impact on the society. And the minimal viable product that we're going to develop is actually to 3D print space antenna. So instead of having those really complex deployable antenna on spacecrafts, which are so messy and so expensive, the idea is you're going to fly in space with your spacecraft, you're going to 3D print your antenna, you're going to check it, okay? You're going to try to qualify it directly in space. If you need, you can tune it like a piano to make sure that you have the proper radio frequency properties, and then you will be able to release it in orbit, right? So the really good thing about it for industry is that they are sure that whatever they release in space will work, because we always have 10, 20, 30% of spacecrafts that have malfunctioned before they are even deployed, right? Because of the crazy launch loads that you have with the rockets. And so once we're going to push that, then we'll be able to do more complex missions. But here, I just wanted to put you this slide because I think, it's really important to be honest with you with the time it takes and the money it takes to be able to do this industrial products, to actually be able to deploy a constellation of small spacecraft in space, and each of them will have a 3D printed antenna attached to them. And so for that, from now to then, it will take between 7 and 9 years. So the first step will be to go back to a zero-G flight, to be able to test some of those technologies in microgravity. Then we're going to go to the big vacuum chamber in Acres Roads, where we're going to actually demonstrate in a full vacuum the 3D printing of active antennas. Right? So we're going to 3D printing them in vacuum. And again, microgravity is not important for 3D printing in space. So we only need to reproduce the vacuum. So we can use this chamber. And this is actually a project I'm currently writing a bit on, and I'm going to go back to it right after the presentation. And so it will cost approximately 1 million. So this is a short project, 18 months. There will be 5 people working on it, really big efforts. And then we're going to be able to actually fly the demonstrator on board a Scottish rocket. And it should go for about 10 million. For 10 million, you will be able to fly the full rocket with about 10 spacecraft on it and the 3D printer. And you will be able to deploy the full constellation. So that might seem like crazy money, right? I will never have that on my bank account. But this is the amount of money it takes to change the way we do space in general. And down the line, we'll be able to do more ambitious missions. But again, to come back on the first part of my presentation, why this thing that I just told you about might actually be useful for society. The thing is, if you can 3D print things in space, which is the most extreme environments we know, right? One of the most extreme we know. It will be actually possible to print things on Earth, anywhere on Earth, in the middle of the desert with the sand, in the middle of an earthquake situation. And this is actually starting to be really, really interesting for off-grid locations, if you want to have off-grid supply chain, for example, or for disaster relief. So again, if we are coming back to the problem for the dialysis machine and filtrating water to avoid diseases, this is exactly the same thing. So you could imagine having an airplane flying over your city where you had a catastrophic earthquake, dropping with a parachute your space 3D printer, and starting to 3D print some water evacuation systems. So you can 3D print motors, you can 3D print pipes and stuff like that, and you will avoid hundreds of thousands of deaths, especially from kids, due to this, this dirty water. And you will also be able to then put back really quickly a telecommunication infrastructure thanks to exact same technology we're going to use for space. So thank you very much for your attention. I hope I was not too long. And if you have any questions, I will be really happy to answer to them. Yes.
Yeah, you talk quite a lot about putting things into space, and I'm particularly thinking about these microsatellites. You usually launch 40 or 50 into space. What happens to them after the batteries run out? Is there a way to sort of get them outboard so that they just burn up in the atmosphere, or are they just like float around?
Yeah, so that depends on what orbit you are putting them. So traditionally, we are classifying orbits by altitude. So you have low Earth orbits, which is, depending on how you classify it, but below maybe like 1,200 kilometers. Then you have new orbit, the medium orbit, and then you have geosynchronous orbits. This has really different heights. So at the end of the life of a spacecraft, if you are in the geosynchronous orbit, it's so far from Earth. It will take you so much energy to bring it back. What we are doing, actually, we are pushing it slightly away, and it's going to go to another orbit that we are calling the graveyard orbit, right? It's going to die there, and it's not going to pollute any workable orbits. And then if it's close enough to Earth, what you're going to do is, if it's below 600 kilometers, you're not going to do anything, because anything that is below 200 kilometers is going to come back to Earth and burn down into the atmosphere within 20 years, due to the residual atmosphere that you have at high altitudes. And if it's in the middle, it's where you have to respect the space law. It was actually an initiative from French people. where you have actually to put in place certain things that, for example, you need to save a bit of carburant inside the spacecraft to be able to do last burn before the end of your mission, to be able to re-enter and burn up into the atmosphere. But this is something really, really important. And the thing that starts to be a big issue is that we are actually starting to detect particles from this disintegration of spacecraft. So in the dust in high altitude, we are starting to find some aluminium and titanium traces which are due to the space segment. So what we are really pushing also at the University of Glasgow is circular economy in space. So the idea is if you are able to 3D print in space, you will be able also to recycle stuff in space. And so the idea is that at some point we will reach a critical mass of things which are 3D printed in space, but you will just be able to recycle everything and not lift off any mass from Earth. So this is the big vision. That's going to take time, but down the line we really want to make sure that we are actually minimizing the amount of things we are bringing to space and the amount of things we are dumping into the atmosphere.
I once heard of an idea about space manufacturing in space in general, and another idea about cloud civilizations in Venus. The thing was they use heat engines that you hang them down, the cloud civilization, because the high temperature and pressure in the Venus surface. So they use that to power the civilization. I don't know, is that far beyond, or is it conceivable with
So the base idea of using the heat of Venus for energy is actually the same principle we are using to get energy for the Mars rovers. It's called the Peltier effect. So if you have electric circuit and one side of it, one lead of it, you are touching something cold, and the other one you are touching something hot, in the middle in your module, you will be able to produce energy. It's exactly like that the RTG, so the nuclear, so the radioisotopic generators are actually working. So it's the big cylinders you see sticking on the back of the Mars rovers, exactly as they work. So theoretically, you could actually power a civilization if you have enough of those Peltier modules. So then you are talking about the civilization in the cloud of Venus. So this is due to the fact that on Venus, at around 40 kilometers of altitude, you have the same pressure and temperature than on Earth on ground. The only difference is that it rains acids. But you could actually live there under bubbles, under domes, on things that are going to float into the atmosphere. So there is actually some NASA studies, you can look at this on the NASA website, where they actually did some designs, what it will take to make a city float on the clouds of Venus. And then you could use your idea for the Peltier effect to produce energy.
Yeah, my idea was to use manufacturing, because Venus has the same the same gravitational acceleration. So you could, get rid of factories on Earth altogether. I don't know.
So I
And
think
the Venus-Earth time, you could make more trips than from Mars to Earth, for example. Venus to Earth is more.
so the issue then is how you're gonna do all the supply chain of raw materials to be able to do the manufacturing.
Yes.
Because on Venus you will not have all the material you need, or you might need to have like a digging expedition done on the surface, which is crazy temperatures, can melt lead. So what you will want to do is to maybe do this manufacturing on the asteroid belt, where there is plenty materials. There's so much materials in the asteroid belt, but if you will bring one big asteroid, it will actually crash the economy on Earth, right? So the idea could be that you could manufacture things directly on the asteroid belt and bring back what you need. Yes?
It would seem that one constraint on the system is the amount of material needed by the 3D printer. If there's any project that's going to construct anything on the moon, has it been considered, would moon dust be a possible material that could be used by the 3D printers?
Yes. So that's actually a really good point, and it's what we are calling in situ resource utilization. So this is a major thing. They are putting so much money into that, and they are doing exactly that. So they are using different technologies. So they are actually trying to tackle different problems. So they are really using the moon dust, so the moon regolith, to do infrastructure things. So basically they are trying to do some bricks and some stuff like that, and actually they are melting the regolith with a laser. So they're actually producing lava, like for a volcano, they are producing lava to actually build structures. And if you're interested about that, there is a really big company in the US which is called Icon, which actually is part of a consortium that's gonna build the first infrastructure on the moon. So they won recently a big NASA contract. We are working with them for one of the projects. It's called Luna 10. You can look at it from DARPA, and they're gonna do exactly that. So that's a good idea.
I think the European Space Agency has been talking about a 3D printed moon base. There's been a lot of work in ESA on building a moon base out of the materials on the moon, sending robotic space vehicles that would create the stuff before the astronauts get there.
That was a really interesting talk. Do you think anyone will try and push the legitimacy of the American patents and see if they'll actually hold up its things? The other question I have is, how would they know? It's not as if they're going to go up and inspect it initially. So do you not just say, oh no, that's our secret thing, black box?
That's a really good point, and that's a discussion I have for the past 4 years with the US Agency. We are putting in place a strategy, because actually what they patented is not a specific type of 3D printer, not something like really precise technology that they will need like a magnifier to check, right?
Yeah.
What they are patenting are things like 3D printing in space,
Yeah.
or uploading a file to your 3D printer, or like stupid things like that, right? They didn't invent 3D printing in space because they had papers 40 years ago on this topic. So those patents are not allowed in Europe or the UK, right? They do not hold anything. But if you are 3D printing something in space, they could technically actually, put you in a trial, and they have so much money. Because the whole value of their company, which is worth billions, is actually on the patents. If they do not have the monopoly of things, the value of their company is going to crash. So what we've been putting in place is actually shifting the way we are presenting 3D printing in space in a different manner, to actually have an argument that we are not actually doing what they are saying we are doing something else, but the end product is the same. So this is, you cannot imagine, I'm an engineer, right? You cannot imagine how frustrating it was for me to sit for weeks with lawyers to try to find the correct words to put in the patents. If you never read the patents, go on Google Patents and have fun, get a nice tea or beer or whatever. You'll see it's another world. It's another world. Yes?
I've got another question about constraints on the system as well as the material for the 3D printer. The 3D printer itself could be a constraint, because if you're using just a model printer, then it's constricted to whatever it can build. What about having an initial 3D printer that would build the actual 3D printer?
So
If you have a smaller printer that its only objective, the only thing it has to achieve is to be able to build the next.
That's that von Neumann machine you're talking about, yeah.
Yeah, it's like a booster rocket, it's like a booster printer that builds.
Yeah, so this is like a self-replicating printers, and there is some design that already exists where they could actually cover, I think they make some funny calculations. So if they were able to 3D print a 3D printer using lunar regolith, they will actually fly a small one with a specific shape, and they will print the next printer with an angle of 90 degrees. For example, if a printer is like that, the next one they're going to print it like that, but they can be super long, right? And so I think in a few days, in a few weeks, they could cover the full surface of the moon with 3D printers. So Yeah, so this is exactly that. So you're actually right in terms of trying to have a 3D printer which is versatile. So this is the ultimate goal. But the big constraint is, because you've seen the prices, the amount of money is crazy, right? If you have the money to fund that, please get my email. But you need actually to get something more simple, more quickly in space. A bit like SpaceX is doing, right? Try to fly something stupid as soon as possible to get some heritage, get some experience, and then complexify as you go. Because this is actually the only way to attract private capital. Because the government will never actually fully fund this thing. You need to actually convince some people with a lot of money to come to you to give their money so you can actually build this experience and then get to this self-replicating 3D printer. Yeah.
I suppose another benefit would be with that booster printer versus what you send into space. The actual design of the new printer doesn't have to be finished, and so we upload it and instruct it to be carried out.
So yeah, so it's reconfigurable 3D printers, and so here you are actually touching something which is really controversial. It's how you actually manufacture electronic components. So the actual limitations is not to build structures, infrastructure, stuff like that, but how do you actually build a chip, a CPU chip. And so there is work that has been done showing that actually the chip will be more efficient if they are manufactured in orbit, not on the moon, because the moon is the worst place to actually do something sensitive, because there's dust everywhere and it's electrostatic, so you're gonna have stuck to you, super easy, right? And it's actually 9 years to get rid of it. But it's gonna be 3D printed in orbit and then put it back down on the moon on Earth, right? But the issue is how do you get from manufacturing a simple layer of diamond, for example, for high efficiency electronic, to actually making a full complicated chip. And so this is something that I'm not foreseeing in the next 10 years, and what I want is to be able to build useful systems within the next 10 years. But, if you have some money, I can collaborate with you.
I think there's a 3D printer on the ISS.
Yes.
Yeah, we haven't got that last year.
I have strong opinions about it.
You don't like it.
This is exactly how you want me to share.
Yeah,
this is exactly the thing. They just took a commercial 3D printer, they put fancy motor on it, fancy glues and stuff, and they flew it and they got millions of it. So when you look at actually the patents, because they're putting a drain of 3D printers, there's nothing new. It's exactly something that you can buy in a shop, you just add some fancy glue to it, and then you're done. So, and it doesn't do anything which is difficult to do, because again, microgravity do not play any role. And it's inside the International Space Station, so there's air around. So they can use fans to control the temperature, to control the airflow and stuff like that. So actually it's, strong opinions. Yes?
You spoke about the Cold War and the digital camera, and we know about rocket technology in World War II and how conflicts kind of drive innovation that way. Then you talked about food security and energy security and tight budgets. Do you or your colleagues or these partnerships have to navigate opportunities with defence companies about potential innovations they could leverage as well? Because there's the more controversial things as well as the altruistic things that come with these and easy money along the way. And
yeah, so that's actually touching a really important point that every space engineers have to ask themselves, because what you see on the left, so this re-entry vehicle, so my goal was to build the next generations of probes that will go to Uranus, that will go to Titan, and stuff like that, right? Big dreams, right? But this technology can actually be used to also construct nuclear weapons. So not the nuclear load inside, but the vehicle that will be around it, right? So actually that's a really big ethical question. So you can take whatever aspect you want, I understand all of them, but in terms of research now, you have to understand that we have a new regulation that has been put in place, which is called trusted research. So first you have an obligation that every time you work in a sensitive area, and you want to publish things, you want to collaborate, you want to give a conference or whatever, you will need to actually submit your presentation on your paper or whatever to the UK government to get an export license. And they can just say no, so they can forbid you to work. So then it depends on what you want to do in your career. Do you want to actually be in contact with people? Do you want to collaborate internationally? Whatever you want to do, but will actually limit the type of project you're gonna want to do. Then the UK is really understanding of this type of situation that is actually a break for innovation. So the big companies are gonna still work for defense industry, but the academia, there's a lot of people which actually do not want to do that. So what they did is they put in place a kind of technology accelerator that they call DASA, D-A-S-A, which is actually something which is funding technologies that could have this dual use. So that could be used for civil and military applications. And the really good thing they did is you can publish everything about it. So the idea for them is to try to leverage of innovation, so low, benchtop demonstration, relevant environment demonstration, but not something that actually will be used directly in a missile, for example, but something lower maturity that can be used both for society and for defense. And so we see a lot of people which are actually working with them on this type of applications. And because you can publish on everything, there's like a lot of people that like that because it's easier, ethically speaking. And then for people that work on the different aspect of things, there's different type of defense. There's defense where you're actually building stuff that can kill people, and you have different stuff that is actually building things which are for surveillance and protection. So here again, we see, for example, a lot of people which are working on novel type of cameras for spacecrafts that will be used for spying, for example, but it can also be used to improve food security or catastrophic event prevention, stuff like that. And so here again, you can make your decision depending on where you want to go. But yeah, so that's a tough decision for most people. That's really easy for some people. Some people just want the money, I guess. But they are pretty rare in academia, because in academia usually you don't really have a market value salary. But yeah, so a really interesting question.
Any more questions? So with that, then we can give another round of applause.
Thank you very much for withstanding my French accent for an hour. I know how big and fun it can be. And I hope you can wish me luck for my bid for tomorrow. Deadline is noon. Wish me luck. Thank you very much.
Thank you.
Thank you very much. But you have a really nice